Everybody. Welcome along this afternoon to the Amazon Web Services and Intel discussion called To Mars and Back, and how NASA uses the AWS Cloud and a lot of good Intel technology to improve all of our life on Earth by the lessons that they learn from their work in space. So my name's Brendan Buffler. I work in the scientific computing team inside AWS, looking after a whole lot of these kinds of workloads along with my teammates. So we've got a few things to discuss this afternoon. We'll be joined by Russ Frumkin from Intel shortly. He's going to talk about some of the stuff that Intel does, to have quite a lot of impact in this space. But before then, we'll get in and we'll have a chat about some of the really cool NASA workloads and some of the stuff that NASA's done, to really exploit some of the advantages of cloud, to do some science and to do some really cool things that they probably couldn't have done otherwise. So it's always a great pleasure and a real honor to be able to support these kinds of work. And as a science guy that works at Amazon, it's one of the things that helps me get out of bed every morning. So anyway, I hope you get a lot out of this, and we'll have a bit of time towards the end for Q&A. And also a little bit of time before then, so I can show you how we actually spin some clusters up, and we'll actually create a few HPC clusters, and I'll show you how we do some of these things. It'll be a fairly short demonstration, but hopefully should give you an idea of this stuff is real, and how we get it into the hands of scientists is the most important thing. So what is cloud computing? If you haven't had any experience with cloud computing before, so it's the on-demand delivery of IT resources, so computers, storage, networking, over the internet typically, with zero upfront costs, no long-term contracts, and pay-as-you-go pricing. So sounds like a mouthful, but the most important parts there is that the most important elements of that is that you get what you pay for what you want, and you can come and go at will. The fact that there is no long-term contracts, no long-term commitment, means that you can shop around and find the best value. You can also change your configuration overnight. You can change your IT needs regularly. And in science, we find this to be particularly important. So, why is Amazon doing the work that we're doing, in this space? We actually think that science is one of the domains of human adventure where we can really have a big impact. And the way that we can have that impact is we can, as a company, we're obsessed with trying to drive down costs. We're also obsessed with trying to bring really cool things, put them in hands of our customers, and watch them do amazingly powerful stuff with them. So, we're really excited by the potential for the impact and the potential for that in this space. Why do scientists like the cloud? And that's actually the bigger question. So scientists, most people that we talk to come to the cloud, and they're really excited about three particular things. We often hear them talk about scale, we talk about agility, and we usually talk about cost. Those are three big topics that we get into conversations with scientists over. Scale is fantastic. I've got a great example to show you in a minute. Of customers that are scaling things to tens of thousands of cores, getting access to the kinds of facilities they just couldn't get access to anywhere else. If you're a scientist and you're used to applying for, access to a national research facility or a national HPC or supercomputer facility, it's pretty common to wait for many, many months while your merit allocation your merit request is being adjudicated. Then you'll typically wait for another couple of months to get access to the machine. You'll have to do a lot of work to get your code ready for that time, and then you'll have a few hours or a few tens of hours on that machine with a few tens or a few thousands of cores to get your work done. If on the other hand, we can bring it into the domain where you can access all of that stuff in the cloud, you can get to those resources straight away at a scale that is really much larger than what a lot of those facilities can offer you, and you can do it for a very, very low cost. It means that you can actually iterate through your scientific problems much, much faster. When we talk to enterprise customers about this model, about the ability to spin up new workloads very quickly, starting with a thought in the morning and leading to a full-blown proof of concept in the afternoon, when we talk to them about that, we often talk about failing fast. And the reason failing fast is important, you want to be able to do an experiment, find out whether it works for you or not, whether that works for your business or for your science. And then if it doesn't work, you want to be able to move on to the next step. You want to be able to iterate quickly. When we talk to scientists, well, that's actually science. That is the nature of the scientific method. So we think that cloud and science really are hand meets glove. So this is the example I was telling you about. This is actually a really cool example, and it's very timely. So just a couple of weeks ago, actually, Fermilab, did an announcement with us about a whole bunch of work that they've been doing to drain lots of CPU cycles out of the cloud for a whole pile of work that they've been doing processing data. This is tier 1 data that they get out of the CMS experiment at the LHC at CERN in Geneva. In fact, I was just there last week and we're talking about these workloads. Everybody is really excited about this. So they peaked out at 58,000 cores. Now that's agility. Agility is being able to scale up to a really massive number and then turn it all off when you're done. And for the time that they had this running, I gather that they increased the amount of tier 1 processing capacity by 50% globally for the CMS experiment. That's a staggering amount of work. And so we'll get into discussing this a little bit when we talk about the spot market. But these 58,000 cores were 58,000 of our spare cores, our unused cores that Fermi was able to exploit at a really low price. And we also think that's pretty exciting for science too. So we talked about Spot. I mentioned that a minute ago. That's working from the right-hand side of this diagram backwards. Spot is actually the area that we think is most exciting in science, because Spot gives you the ability to go in and spend very, very small amounts of money to get access to all of our unused capacity. We like having unused capacity in our regions because it means that we can always say yes to a customer who wants to come along and turn on a workload. So that's important. We always need to maintain that headroom so that we can make sure that the cloud model works for everybody. But being able to utilize all of that spare capacity that has a pretty big driving effect on science. So we think that's going to be pretty popular. The other two models that you'll see on the screen there, of course, is just the on-demand ability. You want to be able to go into the cloud. You want to be able to get access to some resources for a defined period of time. That's the fairly standard model that more than 1 million customers around the world are using. But if you're one of our more than 1 million really regular customers, we would then start talking to you about how to use the reserved instance model so that you could save money for doing that. And it's one of the things that makes us unusual as a company. We often call our customers and say to them, you're spending too much money with us. We'd like to show you how to spend less and achieve the same thing. So that's an unusual thing for us, but it's an unusual thing for most companies, but it's a pretty common thing for us every day of the week. So the cloud's no good unless you're able to store your data in it, and we have a whole range of different storage types, stretching from file-based storage, block storage, so that you can do more sophisticated, customized things inside your workloads that are meaningful to you. You may have a particularly favorite file system that you want to use that has a characteristic that's perfect for your workload. Or you may want to use really super scalable low-cost object storage, and that's Amazon S3 is the best example that we have of that. But there's a whole range of different storage types in the cloud, and in fact, just under the object storage, you'll notice that Amazon S3 is partnered by Amazon Glacier. So Glacier is where you can send your files to go cold, and it's essentially a large archival service. Every single one of these storage platforms has its own characteristics, its own performance profiles, and has its own cost, and all of that's nice and transparent when you come in to use the cloud. Data storage is not much use unless it's secure, and so security is actually our #1 thing that we obsess about. This is something that we really drill into the most. So we spend a lot of time making sure that we can achieve these different governance levels and certifications. You'll see a whole lot of them on the screen that are probably quite familiar to you. And in fact, the comment that Tom Soderstrom, the CTO from JPL, has made, in this regard, is that he thinks that in fact, on his experience building data centers, building clusters, building scientific research facilities over many decades, he actually thinks that he can be even more secure inside the cloud than he can inside his own data centers. And that stands to reason, because we have a very large number of people who are dedicated to looking after cloud security every day. It is a shared responsibility. So Amazon, of course, can't do it all. But what we do is that we offer you a really, really good set of defaults, a great set of, a great structure within which to build your infrastructure. And inside that framework, we are giving you a really good, safe set of defaults that you can know are they're going to avoid allowing you to make any mistakes, that might cost you some security. So anyway, let's get on to talking about Mars, because that's really the fun stuff that we came here today. And in fact, this is one of my favorite topics when it gets into uses of the cloud. So if you're like me, you're somewhere sitting on Earth when Mars Rover Curiosity landed back in August 2012. You were sitting somewhere on Earth, stuck in front of your web browser, watching it all happen live. And it was truly one of the most popular and seminal webcasts that's happened during my lifetime. Was to be sitting there at this moment, when the rover was landing and watching it all unfold. So to do that actually required an enormous amount of infrastructure. NASA came to us a few weeks before the event, and they said, actually, we've just figured out that this is going to break our internet and our workload. It's going to break our facilities. We just don't have the hundreds of servers. And they came to Amazon asking if we could help them. Within 3 or 4 weeks, we'd actually put together a solution with them. We did it iteratively. We did it together. But we'd actually put quite a complex solution for actually being able to, leverage all of the elastic load balancers that we have. We use Route 53 to do some really novel use of some novel tweaking for those load balancers. And then, of course, we just had a massive amount of infrastructure that spun up, and you get the idea of the complexity of that here. You'll notice that we spun up resources in Europe and then also on the west coast and the east coast of the US here. There's a lot of front-end services, there's a lot of back-end storage services, there's a lot of monitoring services there that kept track of all of the traffic, kept track of how many subscribers were coming in to watch all of this activity, and streamed it out to them in real time. And as we needed more resources, more web clients connected, and more people came online, I was sitting watching this in Australia, so it was really early in the morning for me, and I could see how many lights were on in my neighborhood as this thing was happening. I could see the lights going on in people's houses as they were connecting to the net and watching this webcast with me. And as that was happening, our infrastructure was scaling out to cope with the load. And so indeed it was possible for pretty much everybody on the Earth to watch this at the same time. But there's some other stuff in the background of what's, the way that we've supported this project that's actually been simultaneously interesting. It's a little bit less sexy and a little bit more hidden, but it's actually truly the more interesting and more impactful part of this. When it's about a 7 or 8 minute latency or delay, communications delay from NASA, from Mars back down to the Earth, and that's actually at a good time when that's actually good times when we're collinear with the sun. At other parts of the year and other parts of Mars's orbit, we're quite a lot further than that. That latency has a really big impact on decision making and how fast you need to make the decisions to drive the rover to the next place so that it can go and explore its next part of the ground. So when all the images come down and hit the Earth, when they touch down on Earth inside NASA's facility, they move straight to the cloud where they're cleaned up, and then a whole bunch of NASA's algorithms are actually put all of those across all of those images, so that we can extract really key bits of data. We want to be able to see what slope we think the ground is. We want to look at the color of the material on the ground and whether or not it looks too rocky for the rover to pass over, or whether there's an interesting boulder over there or some other interesting formation. And there's a lot of algorithms that assist in that process. Originally, the way that NASA expected the workload or the workflow would happen was that those images would come down, NASA scientists would pore over them for a couple of hours, and then send their commands back up to the probe, back up to the rover to point in the new direction and give it its next tasking. But that turnaround time on the ground, once the data had reached Earth, was too long. And so, in fact, it became really important for these analytics to actually drive to be able to actually drive the decision-making process to help the scientists move there faster. So the NASA engineers and the NASA scientists were able to interpret the data from Mars much faster, so they could make faster decisions and turn around those commands back to Curiosity much faster. So the really good outcome of that is they were able to actually explore a whole lot more terrain on Mars than they expected they would. So, you know, NASA's taken a lot of those lessons that we've learned about geology on Mars and the geography of other planets in the solar system. We've actually, you know, the other thing that NASA's figured out over the last decade or so is it gets really interesting when you turn the telescopes around and look down at the Earth. So that's really the introduction to the orbiting CO2 Observatory. So this is a satellite, or in fact a set of satellites, I gather, that are in a polar polar orbit. These things are the mission is to understand the balancing equation of where the CO2 comes from and where the CO2 goes. And there's a lot of different things that are generating CO2 on the Earth, as we all know. But the real question is, where does the CO2 go? And so this CO2 observatory was built to understand that equation, dig deep into it, and actually understand and to build models so that we could get better modeling, so that we could understand our future here on Earth and understand what climate change would do and what we might be able to do to remediate against it. So the challenge, though, is that NASA had a really large amount of data. This data accumulates massively every day, of course. Every now and again, refinements in their algorithm mean that they want to go back across all the raw data, so they can get back to you know, creating new science data products, you know, level 1 and level 2 data products that scientists can use that are more accurate and better fitting with reality. Unfortunately, reprocessing the data from scratch was taking at least 100 days worth of compute time on the resources that JPL had. And that's really tough, because that actually means that at most you might be able to cycle through some reprocessing, in other words, enhancing your algorithms, maybe only 2 or 3 times a year at most. So NASA came to us again with a problem, and you know, there's a great depiction of the problem spots that they wanted to really dive deep into in terms of the data processing. They really wanted to understand where the CO2 was going in those parts of the world. So they came to us with a problem, and we turned around a solution for them in 37 days. It was a bit of a record. We're pretty happy with ourselves, and really impressed with how NASA was able to use this. So within a few weeks, we'd actually ported all of their code into the cloud. We built the clusters in the cloud, you know, this was a lot of work that one of our guys, Dave Cuthbert, did with NASA to work out to essentially build this infrastructure so that it could scale. Now, at the same time, there were a bunch of performance improvements that we did as well along the way, not just straight from scaling. But in the end, we went from 9,600 cores to 96,000 cores, which is just something that you know, it's difficult to do that anywhere else. And the runtime went from 100 days down to 7 days. Now, the really cool thing about that means that all of the algorithm development and all of the work that NASA's doing to improve their models and optimize them over time, it means that they can iterate it dozens of times a year if they wanted to, rather than once or twice. And as we all know, when we're doing experiments and when, you know, as scientists, we're studying things by trial and error, which is more or less the scientific method, a directed trial and error phase. You need to do a lot of trials, and you need to iterate your model a number of times before you can truly say that you've learned something about the universe. So this really kicked that into a new gear. So again, following this theme, the equation, as you could see in that last thermographic map of the globe, you could see that there was a big red spot over sub-Saharan Africa. There was a big challenge. There was a really big challenge to actually understand where was the CO2 going in sub-Saharan Africa. And that actually required an understanding of the biomass in sub-Saharan Africa. So NASA came back to us with another challenge. And this time we were joined by Intel, who sponsored this effort and also supplied a lot of CPU cores and a lot of technology. And then we assisted our partner Cycle Computing to build a workload that was able to actually take a lot of Earth observation satellite data from a lot of different sources, parse it. We actually managed to. You'll actually be able to see that it's actually quite a lot of image processing that needed to be done here. So when you actually look at this graphic, what you'll notice is each one of these is a shrub. This is a tree in the desert in sub-Saharan Africa. On very dry, arid ground, and of course you'll see that there's a shadow around a lot of the trees. This is just an artifact of the fact that the camera is up in the camera is in an orbiting telescope looking back down at the Earth. So there's a perspective shot here. So a lot of data processing needed to be done to remove the shadows, and then to actually look at the image in different spectrums, multiple different wavelengths, so that we could understand what the nature of the biomass was. That actually allowed us to be able to, it allowed NASA to come up with a measurement for how much biomass was in sub-Saharan Africa. And if you look back here at just at this last snap here, you can see that they actually did it with basically a cost about $80 in the spot market. So we're really excited about that because it actually means that NASA's been able to get an understanding of where the carbon's going in this part of the world, how to balance that giant global equation so that we can understand, hopefully get better models to understand our future. And we did it for $80. Just to make it a little, even a little better, we actually ran all of this in one of our carbon neutral regions in US West. So that's actually an AWS region, a whole pile of AWS infrastructure that's running in a carbon neutral environment. So really, really big thanks to Intel for having supported that project.